next we will look into the topic design for testability and the issues related with it. So, as we have seen in our last lecture that design for testability is a very important part, as it enables easy testing of the system. So, if we want to enhance the testability of a system, so or circuit, so we have to have some extra hardware put into it, so that this testing can be done efficiently. So, this is the content. First we will have a basic introduction, then the testability analysis, then testability basics, scan cell design, scan architecture, scan design rules, design flow, and slowly we will go to special purpose scans and RTL design, etc. So, if we look back during early years, design and test were separate. So, testing was not getting that much importance, in the sense that the designers, once they complete their design and then they tell, okay, this is the design, now you have the testing done on it. So, you design your test vectors, so that this design can be tested, or when this chip comes up, it can be tested. So, the final quality of test was determined by keeping track of number of defective parts shipped to the consumer, to the customer. So, defective parts per million. So, since the test may not be very exhaustive in that case, so it may so happen that many of the good chips, they are marked as bad, and many of the bad chips are marked as good. So, if it is bad chips marked as good, then when it is shipped to the customer, then they will be detected on the field that they are not working properly. As a result, they will get rejected. So, these defective parts per million, that was a measure for doing this thing. So, for small scale design it is okay, because if I have got say the SSI design has got less than 10 gates or so, so then it is easy, because the design is simple. So, in most of the cases we can design these test vectors, even if the test design has been done beforehand. Then came fault simulation. So, fault simulation is actually given the design. So, we can try and the test vector. So, we try to see how many faults are getting covered. So, that way we get some idea about the quality of the test vectors that are applied, but still and we try to do some modification to the test vectors, so that this coverage improves, but getting coverage more than 80% was difficult. So, in our introductory classes we have seen that even with 90% fault coverage, so there is a huge loss in number of defective parts that are sent. So, the 80% is so poor a number. So, this increases the test cost, and this decreased test quality. So, this became a concern, like, so test cost is increasing and this quality of test is decreasing. So, that leads to this design for testability or DFT engineering. There are various testability measures and ad hoc testability enhancement methods that have been used. So, for to improve the testability of a design, as I said that, okay, for a design it may be too complex. So, we cannot access one particular line from primary input. So, we add a multiplexer and put it somewhere, so that the line becomes controllable. So, that way it so that tries to improve the testability in some ad hoc fashion. So, this is one problem. Another problem that another issue was for sequential ATPG. So, if my circuit has got sequential elements like flip flops, then there are some sequential ATPG algorithms that came up that can generate test patterns for the sequential circuits, but still getting more than 90% fault coverage was difficult, because of the same reason that many of the points may not be accessible, and the designers will not allow much modification to their design by introducing these extra multiplexers into the system, because that will affect the critical path delay of the design. So, as a result, so all these ad hoc multiplexer insertion may not be acceptable. So, that gives rise to structured DFT. So, we want to conquer the difficulties in controlling and observing internal states of sequential flip-flop, sequential circuits. So, sequential circuit is a major concern, because they are for testing a particular fault, we need to put some pattern to the internal flip flops. So, that makes it more difficult. So, this putting some value to the internal flip flops becomes difficult. So, you want to observe and control the internal states. So, that becomes difficult. So, what came up is the scan design. So, scan design is the most popular structured DFT approach, because that will put all the flip flops onto a shift register. So, that we can shift in the test patterns and shift out the responses from them. And design for testability has migration, because what happens is that, so even at this point, so it was not sufficient. So, it was observed that we should start the testing process, test generation process from the same point at which we start the design process. So, from gate level to RTL level, this testing process has shifted, it has migrated, so that this design for testability measures can be incorporated easily into the system. We will start with testability analysis. So, testability is a relative measure of the effort or cost of testing a logic circuit. So, how much effort we need to put for testing a logic circuit. So, testability analysis is the process of assessing testability. So, there are various ways by which you can do this testability analysis. One is known as a SQAP approach, which is Sandia controllability observability analysis program. There is another one, probability based testability analysis, so which is more popular, and of course, we have got simulation based analysis. So, all these testability analysis techniques, so they try to measure two values. One is called controllability, another is called observability. So, controllability, it reflects the difficulty of setting a signal line to a required logic value from primary inputs. So, what happens is that if I have got some circuit, then if I want to say put this particular line onto some logic value. Now, I have to, since this line is not directly accessible, so this may be output of some gate, AND gate, and maybe this is getting, there is an OR gate here which is feeding this AND gate. Okay. Now, if this is the circuit, and if I want that, I want to put a value 0 here, then it is very simple that this particular primary input, if I put a 0, then we are through. So, this line will, this point will get a value 0 in a fault free condition. On the other hand, if I want that this line be set to 1, then I have to do many things, because I have to ensure that this line is 1. So, I have to apply 1 here, plus I have to ensure that this line is also 1. Now, for ensuring that this line is 1, I have to make either this line 1, or I have to make the other input of the OR gate 1. So, these requirements are coming. So, if it is deep inside, so this line is only 2 level away from the primary input. So, but still in that case, you see that there is some complexity involved in the setting of that line. So, if it is deep inside the circuit, then it becomes very difficult. It may be almost impossible to set some value for some circuit points. So, if that happens, if we find that many of the points in the circuit, they cannot be set to some desired value by playing with only some of the inputs, some of the primary inputs. So, we say that the controllability is difficult for that. I cannot control that point easily. Similarly, if I want to say observe this value or line, the value that we have in this line, then, and if it goes through some gates, like there is one AND gate here, there is one OR gate here. Okay. Now, you see this AND gate, it can have some input from some other place. Okay. So, there is some logic here which actually feeds this AND gate. Similarly, there is some logic here which feeds this OR gate. Now, if we want to propagate this line to the output, then first of all, since this is an AND gate, so I must somehow have this point to 1, because if this point is 1, then only whatever be the value here will get propagated to this point. And since this is an OR gate, so I must have a value 0 here, so that whatever is value coming here, that is propagated to the output. So, if I can, so again this individual circuit logic part that I have, so they will have their own input and output sets. So, whatever inputs are here, so I should be able to set those inputs in such a fashion that at this point I get a 1. Similarly, whatever inputs are here, so I must be able to set them at proper value, so that I get a 0 here. So, this process may not be very simple. Okay. So, that depends on the number of inputs, number of inputs that we have for the circuit, and for the complexity of this individual logic parts that we have, like say this part and this part, what is the complexity of this logic part. So, based on that only I will be able to decide like whether we can get this value communicated to the output or not. So, that is the observability. So, it reflects the difficulty of propagating the logic value of the signal line to the primary output. So, these are the two important measures that we have, controllability of a point and observability of a point. So, when we have got a circuit with a large number of lines, for each of them we need to have this controllability and observability calculated. In a probability based analysis, so we used to analyze the random testability of the circuit. So, it is so C0S. So, this is called the probability based zero controllability of S. So, what is the probability that I can put a 0 value at S. Similarly, C1S is the 1 controllability of S. So, what is the probability that I can put a 1 value at S, and O of S is the observability probability of S. So, what is the probability that I will be able to observe this value. So, range value. So, this C0, C1 and O. So, they range between 0 and 1, and this condition is true, C0S plus C1 is equal to 1. So, probability of so if it is difficult to control make a line 0. So, this 0 controllability will be high, and then this one will be low. So, 1 controllability will be low. So, let us see how can we calculate this for a probability based analysis. So, for primary input, so 0 controllability is P0, because I can very easily make that primary input line 0 by applying a 0 at the input, and 1 controllability P1 is 1 minus P0. So, if it is coming from some from the environment, so environment will tell us how easy or how difficult it is to set a line to 0. So, that way P0 probability will be coming from there, and P1 probability is 1 minus P0. So, if we assume that this is equiprobable, then this P0 and P1 both of them may be 0.5, but if it comes from some other system as input, then this P0 P1 may not be 0.5. Now, for the AND operation, so AND operation, this 0 controllability is the 1 minus output 1 controllability. So, 0 controllability of an AND gate. Okay. So, let us see, first see the 1 controllability. So, how can I make a 1 here? So, if I want to get a 1 at this point, I have to make both of them as 1. So, this 1 controllability of an AND gate is basically product of input 1 controllabilities. So, if we have got these input 1 controllability, so you take a product, and that will be the input that will be the 1 controllability for the output, and AND gates 0 controllability is naturally 1 minus output 1 controllability. Similarly, for the OR gate, so 0 controllability is product of input 0 controllabilities, because all the inputs must be 0 for the output to be 0, and 1 controllability is 1 minus output 0 controllability. So, in this way, for each type of gate I can say I can define some formula by which we can compute this 0 controllability and 1 controllability of individual gate outputs. Similarly, this buffer, so this is there input 0 this 0 controllability is input 0 controllability, buffer 1 is whatever, buffer does not do any change in the logic. So, input controllability and values, so they get transferred to the output controllability. Now, this XOR gate, so for XOR gate what happens is that if the output has to be 1, then the input A has to be 1, B has to be 0, or A has to be 0, B has to be 1. So, these two cases, these two probabilities are to be summed up, and that gives me 1 controllability, and 1 minus this, that gives us the 0 controllability. Similarly, we have got XNOR. Okay. Now, for the observability values, so primary output, it is definitely observable. So, it is taken as 1. So, this AND gate on NAND gate, so output observability is equal to product of output observability and 1 controllabilities of other inputs. So, So, what happens is that if I have got an AND gate, if I have got one AND gate, so it has got a number of inputs in it. First of all, I should get a, or to get a 1 here, I have to set all these values to 1, and the second thing is that this output. So, this output has to be propagated to some primary output. So, if this chip or if this system has got a number of primary outputs, then this output has to be propagated to some primary output for observation. So, naturally, so we have to have this output observability, and we have to have this the inputs are to be controlled, so that we get ones at this point. So, as a result, we get the formula, it is product of output observability and 1 controllabilities of other inputs. Similarly, or NOR gate, it is again the same thing, product of output observability and 0 controllabilities of other inputs. For NOT gate or buffer, so it is output observability itself is sufficient. So, that is the observability value, because we can if we can get the output observable, then we can just make 1 minus to get the input part. So, they are same. So, similarly, XOR XNOR can be done, and for the stem part. So, if there is a stem, there is a fan out like this, then if this value, so if we want to observe this value, so we can go by any of these branches. So, if again the same thing, if this is the chip and these are the primary output, so this stem may go here. So, the observability value of this stem is the cost of taking this stem to the output. Similarly, this stem will, maybe it is going to this output. So, as a result, so this is the cost of taking this output, this stem output to this primary output. So, you take the maximum of all these branch observability. So, whichever the branch gives me the maximum observability, so that is that easily the stem can be observed. Now, for this DFT design, so there can be ad hoc designs. So, effects are local. So, effects are local and not systematic. So, we just observe something, and accordingly we do some local modifications, so that this testability becomes better. It is not methodical. As I said that this is totally ad hoc. So, it is basically the test engineer. So, consults with the designer and says, can I introduce a line here, or can I introduce a multiplexer here, and if it is possible, then that is introduced. It is difficult to predict, like how much will be the benefit. It is difficult to say, because some points we may not be able to modify. So, that is the problem with ad hoc DFT. On the other hand, if we have structured DFT, so at the design, along with the design itself, so we incorporate this testability hardware, and it is budgeted at that point. So, it is the extra for extra testability. So, I will need this much of extra logic gates, this much of flip flops, or this much of area. So, like that. So, that is put into the budget itself. So, the test engineer can be sure that okay, I will have this much extra things that I can incorporate into the design, yield the desired result. So, naturally, if all those features are incorporated, then possibly I will be able to reach my desired level of yield, and automating the whole process becomes easy. For example, if I have the scan chain, then I can very easily put the desired values at the scan flip flops. So, that way automation becomes easy. So, we will start looking with the ad hoc approaches. So, typical ad hoc techniques are like this, that insert some test point, then we avoid asynchronous set reset for storage elements. So, if there is asynchronous set reset, then when we are trying to design a test pattern, so all on a sudden if a reset pulse comes to the chip to the flip flop, and the flip flop gets reset. So, naturally that cannot be accounted for in the testing process. So, if my design says that if my design can be constrained, that I do not have this asynchronous set reset, then it is better. So, combinational feedback loops. So, combinational feedback loops, if it is there, then it actually makes the circuit circular, and there it makes it sequential circuit. So, sequential test pattern generation is difficult. So, it is better to break those loops Okay. So, as a technique, so we may have some extra component incorporated into the circuit, so that these feedback loops are broken. Redundant logic we like to avoid, because that will help us in generating test patterns. We can detect more, the faults will become more non-equivalent. As a result, they can be detected. However, this redundant logic removal, so this is not always advisable, because designers, to avoid this hazard and glitches, they may like to put some extra gates in the circuit which are actually redundant, but that helps avoiding them. So, that way this redundant logic removal, though these test engineers will ask for that, the design engineers may be telling the other way. Then asynchronous logic. So, asynchronous logic, if we can ignore, then we know that the entire operation is synchronous with some clock signal. So, my testing is can be concentrated on this individual clock transitions only. So, this cancel shifting and all that, so that can be affected easily, but asynchronous system does not have clock. So, as a result, it becomes difficult to control the overall test session. And if I am allowed to partition a large circuit into small blocks, so that can be helpful, because it will help us to concentrate on smaller parts of the circuit. So, as a result, the testing process may be simpler. So, in fact, what happens is that this test generation process algorithms particularly, so they are all NP hard in nature. This problems is NP hard in nature, and for NP hard problems, the difficulty is that we have to use heuristic methods, and heuristic methods, they normally work well if the input size is small. So, if the input size is small, if the input circuit is small, then this NP hard algorithms, this NP hard problem for the heuristic algorithms, they can give reasonably good result. So, if we can partition into small blocks, so it is easy, but again the same thing, it depends whether the design can be partitioned or not. It is very much design specific, and it requires concurrence from the designer. So, the ad hoc test point insertion. So, suppose this is the situation. So, this is the logic circuit, and there is a point which is these are some low observability points. So, A, B and C. So, they are 3 nodes. So, these 3 nodes, they are not very much observable. So, what is done? We put them into, we introduce a structure like this, which is known as observation shift register. So, in this observation shift register, so we have got this type of cells, OP cells. So, the OP1, OP2 and OP3, they actually form a shift register. So, what is happening is that, so if you look into one particular such cell, say the OP2 cell, so it has got one input from this low observability node B, another input is coming from this OP1 cell, and then it is going to the D flip flop through this multiplexer, and this from this D flip flop it is going to this scan out to this scan out point or serial out point or shift out point, and that goes to the shift input of this OP3. Now, if we are if we apply some clock, so what will happen? These low observability points A, B and C, they will get captured onto these 3 flip flops, so corresponding to OP1, OP2 and OP3. Now, if you enable this serial shift enable or serial enable, whatever you call it, and then apply some clock, then so if you look into this multiplexer, when this AC line is equal to 1, whatever is coming on the SI line, so that will go through it. So, this after 1 clock, so this SO line of this OP3, that is this node C, is available at the output. After 1 clock pulse, this OP2's SO this Q bit will be coming into this OP3's Q bit, so as a SO Q bit, so you will get it on the SO line. So, this B can be observed after 1 clock cycle, similarly A can be observed after 2 cycles. So, all the low observability points that we have in the system, so we can tap from those points and put them onto this observation shift register, and this observation shift register can be shifted by applying clock to it in a serial shift mode, and then we can get all these outputs. So, the observability of the circuit is enhanced by introducing these observability points. Another issue is the controllability. So, suppose I have got this type of situation. So, this node B is a low controllability node. Similarly, for this A and C also we have got similar situation. So, this is the point that we want to control. Similarly, here also we have a point that we want to control. So, original connection was as in the dotted line. Okay. So, this was the original connection. Now, if we want to put some value here, externally we want to put some value here. So, we again take help of some shift register. So, what we do? So, this line is this connection is broken from source to destination of node B. So, this connection is broken, and this from this source the line is taken and it is connected to the data input of this CP2 cell. Now, when this for the normal operation of the system, so this test mode, this TM input is 0. As a result, this data input line will be coming from here and it will be going through this DO line to the destination. So, this multiplexer will be transparent. So, from DI line it will come to DO line and it will go to destination. So, as if this connection gets established. Now, in the test mode, suppose we want to set some value to this point, okay, to this destination of node B. So, what we do, somehow we set this flip flop Q to the desired value and then this test mode signal is made equal to 1. So, what will happen, this Q will be available, this Q will be available at DO and then that will go to this destination. So, whatever pattern, whatever bit we wanted to put at node B's destination, so that will be done. Now, you see that suppose depending upon our requirement, so the same structure is repeated in CP1 and CP3. Now, depending upon our requirement, suppose we want to put this this node A at value 1, node B at value 0 and node C at value 1. So, what we do, first we apply this CP input and in the CP input we give it clock. So, if you see this SI, so this SI input is whatever, if we give a clock to this flip flop, then this flip flop will get the value. So, initially this TM value is made equal to 0, but through this CP input line we serially shift in the pattern 101 onto the 3 flip flops of this CP cells. After they have been shifted, then we apply this TM line, we make this TM line equal to 1. As a result, these connections get broken. This connection is not established, this connection is no more there, which was taken for normal operations. So, it was going through this multiplexer like this. Now, once this TM line is made equal to 1, so this Q output will be coming here and it will go via this DO line to the destination. So, this pattern 101 that we wanted to apply at the 3 control nodes A, B and C, that can be done. Okay. So, this is the control test point insertion mechanism. So, using this type of shift register, observability observation shift register and this control shift register. So, we can observe and control individual points of this of the circuit that we want to see. So, we will continue in the next lecture.